This is I guess my presentation on Gotta Go Fast, real quick, which is essentially a post-mortem on client-side file processing using WebAssembly. So a little bit about me. I work at Janaya. I'm MC 706 everywhere. I've written about topics like this and other topics on my website at mc706.io. Passionate about technology in all of its forms, so I write about it in different places and occasionally give presentations on it. So what we'll be covering. So this is, like I said, a post-mortem of using client-side file processing and squeezing more performance out of the browser. I'll go over the problem we were trying to solve, what the naive approach we took at it. We went through a good portion of the JavaScript ecosystem trying to find a better way of doing it. After falling short in JavaScript, we moved into WebAssembly and Rust. And then we moved on to WebAssembly and WebWorkers. And I'll go over some gotchas, some of the things we learned, and the outcome of trying to solve this problem. So the problem we have, this was a work problem. So one of our Janaya is, for those who are unfamiliar, is a marketing tech startup. We are in Conshohocken. We help marketers have more intelligent and safe communications with the people they're marketing to, especially in the major life purchase market. Our largest product is a product that allows large marketing people to essentially give us a list of their prospects, and we will tell them when prospects might start a consumer shopping journey. So if you're looking for a house, we can tell when you might be looking for a mortgage just through our network of data partners. At our core, we have a very strong ethical stance on not having personal identifiable information. So all of the data that Janaya has on everything. So we've witnessed roughly 11 billion consumer shopping events over the past 10 years at this point. We do not have a single shred of personally identifiable information anywhere in our system. So as soon as any of the data hits our system, it is already hashed, and we're just storing hashes of data. So essentially, when a customer is asking, hey, is Ryan shopping for a mortgage? What they have to do is they would have to hash my email address or my phone number and ask, is this hash shopping for a mortgage? Because our major clients are all marketing firms or marketing departments of things like banks or insurance companies, our actual users are not very technical. It is not hard to ask another developer, can you send me the MD5 hash of a particular thing? It is really hard to ask a marketing associate to hash their 10 million line file and say, hey, can you hash all of the emails and phones and make sure that you lowercase them and restrict out any invalid characters first. So we also had a number of we were taking our data in as a CSV. All of the PII, again, needed to be cleaned and hashed. Some of the columns needed to be in a particular format, so we allowed you to also pass in some of the unique identifiers we have in our system in the form of a UUID. It needed to be in the string representation of UUID. We had some other pass-through information, so you can pass like market segment and stuff into the file and allow it to come out the other end of our system so that you could do marketing-based routing. But telling people how to do that was a little bit hard. And then generally when people are dealing with CSVs, they reach for Excel. When you're dealing with hashes, Excel tries to interpret hashes in a particular way, and it can often mangle them. So like, hey, I have this thing and it has a leading 0, and I'm going to drop that 0 for you, which is in the hash sum world changes the value. So we were having a lot of trouble with our customers trying to figure out how to actually give us the data so they could get value out of it. We wanted to, and then the last step that was having trouble for our customers was once they built a file, or they thought they built the file, they would put it on an SFTP server, and then a script would pick it up and validate their file. This involved booting a pretty large EMR cluster and running a number of validation jobs. And then it would eventually drop a results of did you pass validation or not back on the SFTP server. But this process could potentially take hours, especially for larger clients who had roughly 30 million consumers in the file they were monitoring. This usability problem was leading a time to value for our customers of they bought the product and it might be weeks or months before they could start getting value out of the product. So this was something we were trying to solve. As a tech lead, it was very front and center on this is something we want to derive value or fix. So it wasn't necessarily, we as a business didn't know the best way of solving it. We had some theories. So the very first approach we took actually was the result of a hackathon. So we were having a hackathon on how can we essentially spend some time away from the rest of our day jobs to take a look at what are some ways that we can solve problems in interesting ways. I wrote a little tiny Elm app as a user interface that allowed users to essentially upload a file into their browser and do hashing of data. It looked a little something like this. You could upload your file. It showed you a preview of your file. You could then map the file, the columns to, hey, we want to drop some of these. Hey, handle this as an email, which would then clean and hash that column as an email. And then it would output them back a processed file. This actually won the hackathon for both innovation and helping provide customer value. But it had some very obvious drawbacks. The first one was the test file we used during our hackathon demo was roughly 30,000 rows, and it took 7 seconds to complete. That doesn't sound terrible, but as far as performance-wise, that means we were averaging somewhere between 4,000 and 5,000 rows per second. In practicality, our average customer file is roughly 250,000 records. And our largest file still to date is 30 million records. At that 4,000 to 5,000 rows per second rate, it would take roughly 50 seconds on average, which isn't great. And it would take an hour and 40 minutes for our maximum size file, which isn't necessarily a user experience you want to have someone sit through. What's worse is that hashing process blocked the main thread of the browser, so the application froze for the duration of file processing. That was no bueno. Especially 50 seconds is probably longer than anyone would ever reasonably sit and expect their browser to still be working. An hour and 40 minutes was a non-starter. And this started, how do we do this but faster? So we started down this optimization path on how can we make, we've proven out that this is a thing that potentially can be done and it can provide a lot of value, like showing our hackathon project to a few customers, they loved it. But at those speeds, it was not a feasible solution. So preparing for an optimization problem, some of the best practices we were following was you need to make sure that you have repeatable tests to make sure you're testing something and that it's consistent. Measure multiple times because there's a bunch of things that may be out of your control that impact what's going on. Like if you have processes running in the background and your CPU is down for some reason, there's a lot of things that go on in browsers. So measuring performance is not, you don't have the same tools you have when you're doing something locally that you can essentially build a sandbox and say, this is exactly the performance profile. So making sure that you measured multiple times and to account for that variance in browsers. And then making sure that performance scaled. So when small files versus big files, what does that look like? And if we can go fast, does it still continue to work when you go bigger? So we built a test setup. I wrote a real quick Python script using the Faker library to just generate random data that looked like the data that we would need. So I say random, I say I need a first name, a last name, I need email fields, I need phone fields. Generate me one actual faked emails and actual faked phone numbers. So we generated a number of different file size sets, one being 1,000, or essentially going up through the orders of magnitude, just to essentially say how does what any given algorithm or library or implementation perform at each of these record set sizes. And then we wanted to run each test 5 times for each setup and use the average to actually say this is how well a implementation performed. So the first step was, okay, Elm is great. It's really fun to write in. It makes fast and unbeatable programs, but it's probably not the fastest thing out there as far as JavaScript goes, because after all, Elm does compile to JavaScript. So we looked into the JavaScript ecosystem, and there's a library called PapaParse, which bills itself as a powerful in-browser parser, CSV parser for big boys and girls. It has a lot of configuration options, including WebWorkers and file streaming, and they have this very large benchmark page that shows that claims they are the fastest JavaScript parsing library out there. So we took a look at it. We tested some configurations. The first thing we did was, out of the box, how well does PapaParse perform? So that's just you import PapaParse and call papa.parse. And then, so we essentially took that hackathon project, removed the file processing module out of it, and replaced it with a PapaParse module. And then did timings on either side of, okay, we still are using the UI to do the configuration of how we want your file to be mapped. And then how long does it take for a file to be mapped appropriately? And so for our first set of test results, PapaParse, here were the results. We ran at roughly around 35 to 36,000 rows per second, which is roughly 7 times faster than the Elm code. We did run into a problem at 10 million records. This 10 million record file is 1.1 gigabytes of data, and JavaScript ran out of memory while trying to parse. So given that our maximum file size is 30 million, which would be roughly 3.3-ish gigabytes, we knew that this isn't a viable option, but it gave us a starting place. Luckily, PapaParse has a bunch of other configuration options. So we did some performance tuning. We tried, I think, 15 different sets of configurations. The other problem with PapaParse was this out-of-the-box call was also, it was in memory, which is why it ran out of memory. And it also blocked the page. So still not great. After testing a bunch of the different configurations for PapaParse, we found the best one to be this streaming. You set streaming is to true and WebWorkers equals to true. What streaming does is it will only read the file into memory one chunk at a time and process the chunks. So that prevents you from running out of memory. And what the WebWorkers essentially loads the part that does the parsing into a WebWorker in JavaScript, so it doesn't block the main thread. It turned out to be somewhat slower. At its peak on very large files, it essentially averaged out to be the same, but overall, for the smaller cases, it was slightly slower. For the larger cases, it ended up being about the same in the long run. But we could process files up to that 10 million, and we eventually did try a 30 million record file run, and they did process successfully. So again, it was slightly slower than the in-memory version, but it could large main files and didn't block the thread. Booting the worker took a little bit of time, which is why you see it's almost half as fast as the in-memory call on the smaller files, because we're not amortizing that time over a larger file. So our score so far, we had our naive Elm approach, which was around 5,000 records per second. For our average case, we were talking around 50 seconds. For the 30 million case, that would take an hour and 40 minutes, but it blocked. Default PapaParse out of the box was roughly 5 or 7 times as fast. It ran in around 7 seconds. It means that it would be around 13 minutes, but it's still blocked. But the most optimized version of PapaParse we could find was slightly slower, would take around 14 minutes for our max, but it didn't block the page, and we could essentially emit progress events, so we could show a progress bar. At this point, with PapaParse saying that they're by far the fastest parsing library out there, and looking at the benchmarks, we had essentially assumed that we had run out of run speed in the JavaScript ecosystem. And so that's when we got a little bit creative and we started looking at WebAssembly. WebAssembly, or also known as Wasm, is a binary instruction format for stack-based virtual machine. It is designed as a portable compilation target for programming languages, enabling deployment on the web for client and server applications. Essentially, what that's saying is you can take another programming language like a C# with Blazor or Java or C++ or Rust and compile that to a target that runs in the browser underneath the JavaScript engine. So whenever you execute JavaScript in Chrome, Chrome's JavaScript engine has to interpret what you wrote, parse it into instructions, and then run that on your computer to produce a result. What WebAssembly allows you to do is go underneath the JavaScript interpreter and go directly to the execution engine. What this gives you is this near native speed. So you end up with smaller instruction files. They load very quickly because they don't need to be interpreted. And their execution time aims to be native speed by taking advantage of some hardware capabilities. So if WebAssembly allows us to get to near native speed of these programming languages, we went after what we thought to be the easiest fast programming language to work in. So Rust self-bills as a language empowering everyone to build reliable and efficient software. And it's pretty fast. It is blazing fast and memory efficient. It has no runtime or garbage collector. And it bills itself as being incredibly fast. I remember reading the paper when Firefox rewrote Firefox in Rust, and it just out of the box got 35% faster. In the global benchmarks of what is the fast programming language, it only sometimes comes in slower than C++ and regularly outruns C. JavaScript isn't even on this spectrum at this point. We are too far to the fastest side of programming languages, but Rust is pretty, as far as programming languages that have higher level concepts that are easy to program in, it is about as fast as you can get. And people seem to like this pairing because there's a rather large community around WebAssembly and Rust community. There's a library out there called Wasm Pack, which allows you to essentially define Rust using Wasm bind gen. And Wasm Pack will build your Rust modules into WebAssembly modules that can be easily imported by Webpack. So it is essentially designed to create publishable Rust modules for the WebAssembly ecosystem. And all you have to do to use it is Rust has, you decorate a public function on your Rust module with this Wasm bind gen decorator. This decorator in Rust, it's a compiler macro. And it essentially makes any public functions in your Rust callable from JavaScript on your exported Wasm. The other benefit is most of the crates or the packages in Rust can easily be loaded into Wasm modules safely. This means that I could use a standard CSV, the standard Rust CSV parsing library. I could use the standard MD5 hashing library. When all was said and done, the Rust code to do the equivalent thing that PapaParse was doing and the hashing functions was roughly 80 lines of code. And then Wasm bindgen also gives us some shared types between Rust and JavaScript. So you have to essentially define the interface because Rust is strictly typed. And some of those are things like file reader, which is a browser API. So essentially, Wasm bindgen knows how to ingest a file reader object from JavaScript so that you don't need to pass the entire contents of a file as a string back and forth. So how did it perform? Out of the box, it was blazing fast. So previously, we were getting roughly 35,000 with PapaParse. For the medium and larger sized files, we were running roughly twice as fast. With another caveat that the 10 million file didn't run. And after doing some extensive research, because apparently not a lot of people try to load tons of data into WebAssembly, whenever you start a WebAssembly module and it boots up this runtime sandbox for WebAssembly, Chrome and other browsers pre-allocate a given memory space. And that has something to do with how Rust likes contiguous memory, and that's how it gains some of its speed. So it's essentially allocating a block of memory for your WebAssembly sandbox to run in safely. But it doesn't know about like your runtime needs. So that's not a dynamically sized sandbox. So running a 1.1 gigabyte file through that sandbox ended up running out of memory, and it essentially halts the execution of your WebAssembly module. So that was less than ideal, which means that it still wasn't great. I was also surprised, given that WebAssembly isn't running in the main thread, the call waiting for a response from WebAssembly did block the main thread. So that, despite it being way faster, or roughly 2 times as fast as the fastest we could go in JavaScript, it was now behaving with that, hey, it's going to block the main thread again. And that's not great. And we still ran into this problem of we can't load super large files into it. And then there was also a little bit of, you'll see that the 1K file is significantly slower than all the rest of them. And that is, again, the load time of Wasm. So when Chrome or your browser is allocating that WebAssembly sandbox for your code to run in, that takes a little bit of time, and that doesn't pay back until you're dealing with slightly larger files. So we immediately went to address this blocking the main thread, because that's no bueno. So it turns out you can just load your WebAssembly module into a web worker. And it roughly doesn't impact performance all that much. It does start slightly slower, but overall, it means that essentially wrapping it in a web worker means that the thread that's waiting for WebAssembly to come back is not the main thread. So we got roughly the same performance, and running it in a web worker did not change how WebAssembly allocates memory, but it did solve our main thread blocking issue. And workers also add a tiny bit of time to when things start up. But a lot of times in the browser, you can hide that behind other things like page loads. So our scoreboard so far, Rust and straight WebAssembly ran roughly twice as fast, which means that our 30 million line file can take just under 7 minutes, but it was blocking. Throwing in workers on top of it essentially was the same runtime, but it didn't block. Which at this, but we still had the problem that we couldn't load large files. And we had the problem that 7 minutes is much better than an hour and 40 minutes, or an hour and 40, but it's still not a great user experience. So we wanted more speed. So we started looking around, and we found a solution to both of our problems. So we have this WebAssembly module running in a web worker, which is a separate thread to the main thread, we could break up a big file into a bunch of small files, each of which are smaller than our maximum size limit, and process them in parallel and collect the results at the end. So that allows us to, we essentially boot multiple workers and multiple WebAssembly modules, break the file into smaller pieces, process in parallel. That allows us to get around the out-of-memory problem and allows us to increase some of our speed. We ran into a small problem that breaking up CSVs is not something you can trivially just chunk a file into 4 different pieces, because if you chunk a CSV record in the middle of a row, or you end up with 2 invalid rows that fail to parse. So essentially, we came up with a clever JavaScript snippet that goes through and finds roughly file chunk sizes, and then finds the nearest new line to break on that, and then returns new file blobs. Overall, it was not that big of a thing. So essentially, we have a split file function that takes some maximum chunk size that we want, or some target chunk size that we want, and then tries to break it into even pieces of it or 80 pieces of it. And then essentially this one, it strips off the header of the CSV. It then goes and seeks forward in the file, the expected file chunk size, and then seeks backwards for a new line, and then emits a new file blob, reappending the header. So essentially, if we have a 1,000,000-line file and we want 10 chunks, we'll get with 10 smaller CSV files, all with the same header, that allows us to essentially process them in any order that we want. How did this perform? And mostly due to parallelism. At the smallest levels, it didn't go any faster. And that's mostly because that file fit inside of the chunk size. So it did no different than its previous one. However, as the files got bigger and we ended up chunking the files more, we saw more parallelism occurring and more parallel processing of the file, which meant a lot more speed. It doesn't block. Again, we're working in entirely web workers and non the main thread. We did notice there is a very noticeable spike in CPU usage because we are using a lot more processing power, using potentially 80 different threads running WebAssembly and Rust. The first time I tried to demo this on a Zoom call, it crashed Zoom. So it does a lot of work. So that brings us to the final piece of our scoreboard, where we got, with the parallelism, we got roughly, again, 3 times as fast, which means our 250,000-line file process, our average case was less than a second. Our largest case was around 2 minutes. And most of the customers who were loading in these 3 or 4 gig files who had 30 million rows, it was easy to add the messaging around to say, this might take a second, or maybe a minute or 2. But we were able to essentially take this large file specification and feed it through the browser and process in what our initial thing would have taken hours in roughly 2 minutes. Charting out all of those results across file sizes and speeds, you can see that I excluded the naive implementation in Elm because it would be a flat line at the bottom here due to scale. You can see the 2 PapaParse, one of them in memory that can't quite get to 10 million, and the streaming worker that essentially levels out at that 35,000 records per second number. We could see our 2 WebAssembly and WebAssembly with a worker going up to around that 75,000 records per second number, but halting before they got to that 10 million record number. And then that chunked Wasm worker piece that allowed us to essentially break up the file and divide and conquer using the power of WebAssembly, and how as the file got bigger, it just got faster because we ended up with more parallelism. We did some experiments where we would back away from that approach and just try to chunk it into 80 pieces. That ended up being far slower. Like the work to chunk the file ended up being more expensive than the performance gains that we were getting. And for large file, like the 250,000 line file finished in a second, we figured that was fast enough. So we didn't need to boot more workers to do more work. So essentially, this allowed us to scale with how much work we needed to do, which ended up being like an ideal situation for what we were trying to do. Is we didn't need to process a 10K file in 2 milliseconds or 10 milliseconds instead of 100 milliseconds, because the user's not going to notice anyway. But the difference between a million and a 10 million line file, like then we do want to add the more workers. So we found that that scaling model ended up paying us back the best. Some gotchas. Figuring out the types to pass between JavaScript and WebAssembly is really hard. Out of the box, it supports strings. If you've ever worked with Rust, Rust has two types of strings. And there are strings and string slices, and one is heap allocated, the other is stack allocated, and they don't share what operations you can do between them. So that has a lot to do with how Rust isn't garbage collected and memory management, and trying to prevent some of the dangerous things you can do with strings from being expressible in Rust. That not being in JavaScript and being in Rust makes going back and forth between them a little bit tricky. Out of the box, WebAssembly and Rust only support certain types of strings and JavaScript native types. So number, which parse into int and float types, or uint, int, and float types reasonably in Rust, and Boolean. Passing arrays and objects. Rust has arrays, but they're fixed length, so they don't behave the same way as arrays do. What you're probably looking for is vector, which doesn't have indexing. So there's a bunch of different trade-offs on going back and forth between types. Out of the box, this is very hard. There is an option when you're compiling your Wasm pack and Wasm bindgen library to essentially pass everything as JSON back and forth and do serialization and deserialization on either side. This roughly doubled the size of the bundle and adds roughly 6 milliseconds of overhead to every single call. So it significantly impacted performance on the lower side. We could have been roughly double the speed on smaller files when processing Wasm if we didn't need object serialization in either direction. So if you were doing pure math or pure calculation-based stuff that you only needed to pass numbers back and forth, you can get rid of a lot of that speed or that performance overhead by not serializing data in and out of Wasm. I spoke to it a little bit earlier. Wasm memory management is weird. There are some options you can pass, but when you're compiling your module, you're too greedy on how much memory you try to grab, your Wasm module just won't load. Depending on how Wasm Pack has a number of different ways that you can compile your WebAssembly module. You can compile it as an ES6 module. You can compile it as a web bundle. You can compile it as a targetable for TypeScript. So there's a bunch of different ways that you can, a bunch of different compile targets for WebAssembly. Not all of them work in all of the browsers. So kind of figuring out what matrix you were looking for was tricky. Firefox does not allow Wasm to be loaded into WebWorkers running in module mode. There is an open bug in Firefox that has been open for 3 years. We did not try to get around this. Instead, in our web application, we ended up just feature detecting. We ended up with a very small Wasm module that we tried to load in, and it called back to the JavaScript thread and said, yes, I support it, or no, I don't. And that turned on the section of the UI that allowed this. So if Firefox eventually gets its stuff together and it can support WebAssembly or in WebWorkers in module mode, that bit of code can just go away. But for now, that was a really weird and frustrating piece on the standards in the WebAssembly ecosystem are not completely set yet. What did this mean for our team? So we added a ton of extra UX on top of the file builder. Besides that simple hackathon project, we added a lot more validation, testing, refactoring, and we ended up deploying a version of the file builder to our user interface. In the weeks since we've done that, we went from an average time to value for new customers, which was previously on the order of weeks to months, down to minutes. We actually had one of our returning customers call customer support because they literally said there's no way it can be that easy. Like we were spending weeks and months prepping these file uploads previously, working with our IT teams. And now we were able to do it ourselves in the browser in a matter of minutes. Lessons learned, WebAssembly gives you a ton of extra power in the browser. So if you find JavaScript lacking in power, I think WebAssembly is a good thing to reach for. Rust is a solid choice for Wasm. There's a lot of library support, a lot of documentation. There's a good community around it. The Wasm module that we ended up with, even with serialization, deserialization, hashing, and a complete CSV library built in, the bundle size ended up only being around 100K. For reference, jQuery is around 200K. And then if you want to squeeze a ton of extra performance out of something, absolutely use WebWorkers. While we got around roughly twice as fast going from JavaScript to WebAssembly, going from WebAssembly without threaded workers to with threaded workers was roughly a 3x performance increase. And then from a general user interface thing and seeing how our users ended up interacting with it, tight iteration loops are not only good for developers, they're great for end users. So previously they had to wait weeks to months to finally implement their file upload and get everything running. And when that got down into minutes, we saw customers interacting with our application more and using it in new, different ways because it was no longer a barrier to entry. That's all I have. If anybody has questions. Oh, I have some questions in the Discord. As you deploy this file validation behavior to users, they get quicker feedback that the file was valid. Do they have to parse the file again at the server level? So our server-side code is running in Spark, so we don't necessarily have access to Node. We could use the Wasm code in a Node server to do that sort of validation. But currently that Rust code isn't being reused. We are taking a look at Rust also has foreign function interfaces with Python. So we might be able to create a UDF function in Spark that wraps a Rust FFI call that does that same validation. And then we can have one source of truth for both server-side validation and client-side validation. Mobile web have same behavior characteristics as desktop web. The portion of the application we were going for did not have a mobile experience. We don't expect users to try to load and map a 30 million line file on their phone. I imagine the sandbox environment for WebAssembly on mobile is much smaller. So I probably wouldn't be trying to load files into the WebAssembly sandbox the same way that you can do in a browser, in a desktop browser. But I think you can get a lot of speed out of just the calculation side, and WebAssembly is supported on mobile browsers. There is if you just Google, so do you have any recommendations for Rust and/or Wasm books and learning materials that I personally enjoyed? Yes, the Wasm pack documentation goes through and has a Git book guide on how to go through, like, from simple math examples to more complex things that actually pull in JavaScript APIs. So WebAssembly is actually far more powerful than what we've been using in this sandbox mode. While WebAssembly doesn't have direct access to the DOM, it does through some callbacks. So there's a few WebAssembly frameworks out there. I think YEW is one of them that actually allow you to write full-scale applications that run multi-threaded in the browser in WebAssembly. And they essentially wrap a small JavaScript ecosystem that allow them to essentially build the virtual DOM in Rust and apply it at the JavaScript layer. So that allows you to do some high performance multi-threaded applications in the browser without having to deal with some of the weird serialization callbacks. Because if you're doing all of the work in the Rust side, you don't necessarily need to like transfer it back and forth between JavaScript. Essentially, JavaScript calls the Rust produces virtual DOM diffs, and then the JavaScript side just applies them to the page. So there's a lot more things you can move towards in that direction. Did custom machines become a limitation for a high CPU usage? We haven't had anybody complain yet. We haven't had someone try to upload a 30 million line file as a customer yet. We have done it on our machine. So, but that being said, we do run Mac Pros or MacBook Pros. So I would expect if someone was running a cheap Windows machine and you tried to do a 30 million line file, Chrome might allocate you less space. And it might bottleneck much faster on the CPU side. But the vast majority, I think only 1% of our files were larger than that 10 million mark. And I think only like 3% of our files were larger than that 1 million mark. So with the vast majority of them being on the order of roughly 100 megs, we find that most of the computers that are running Java are running Chrome that allowing for things like WebAssembly to be run had enough memory to load the files that large into memory, which probably goes to say we probably could have stopped long before we got to the final destination we went to. But we had this, we wanted to reach for those larger customer files. So I expect that it will be a limitation in very rare cases where we have a combination of customers with massive customer bases and very poor or cheap computers. But we haven't run into it yet. And I think the vast majority of our users are running those medium-sized files that it won't be as much of a problem for. Any other questions? Absolutely, it was a blast. It was a lot of fun, like going through and like playing and trying to find out new web technologies to solve a problem, and that's certainly something I'm passionate about. Finding really cool technology to solve cool problems. So, thanks for coming.